is that the last thing I want to cover is I want to talk about the meaning of a joule of work. So let's go look at this thing here. So one of the things that we know is that work and energy are two sides of the same energy coin. What do I mean that? Well, if you look at a quarter has heads and it has tail. I mean, they're both different, but they're still the same quarter. You need both sides in order for them to work. The same thing happens here. There's part of the same energy coin, and therefore they have the same energy unit. And here's what we know. So the units are joules, and this is in the metric system. But are calories in the United States. And then here, this system is the English or the imperial system. So now what we find here is that there's a conversion factor between these two. In other words, we have something that we typically call a little calorie. And the way we write a little calorie is we write it with a little c here. And a little c, a lot of times people will just go little cal like that. But in our units, we typically just write c, excuse me. So this will then be 4.186 joules. So a little calorie looks like that. However, that's not really what we typically use in science. And in science, we don't use little calories typically. We use the big calorie. And the big calorie is written with the capital C here. And this guy is equal to 1.86 kilocalories. And this, by definition, is what we call one food calorie. Okay, so one big food calorie is 1,000 little ones, but it's equal to 4.2 kilojoules. So I would say that this is the standard unit of work/energy everywhere. So now what we want to do here is to get a feel for that. I want to go through an example. And in this example, we want to get a feel for a McDonald's chocolate shake. So when you Google this thing, this guy comes in at a whopping 1160 food calories. Let me tell you, a lot of us, it's recommended that we only have 2,000 calories per day. Yeah, this guy, one of those milkshakes, and I mean, you've almost exhausted all of your calories for the day if you play that game. So now, after drinking the milkshake, by the way, with Thanksgiving being tomorrow, maybe one of the things that you do here is that you overeat, right? So after drinking the milkshake, you feel guilty, right? You feel guilty and feel the need to work it off. You feel guilty. So then you go to the gym, right? So now at the gym, you weightlift to burn off the calories. Okay, what does that mean? So let's say here that we're going to say that you're going to do bench press. You're going to bench press 160 pounds, which is equal to roughly 700 newtons or 710. So this is your choice. So why did I pick bench press? Because it's easy. It's easy to draw the picture for a bench press. That's the only reason. So now here's the big question. How many reps are required to burn off the milk shake calories? I hear that all the time. Now remember that milkshake has, roughly 1,200 calories. That's a whopper. Okay, so what I did here is that I imagined that I'm the one that's doing the lifting. So because I was able to measure the distance that I lift up a bar. So here we go. So Carlos does the lifting of the weights. So what do I know about that? Well, I have a plate, and this is my plate, and this is the one that I'm going to lift up. That's part of the bench press. And so what I'm going to do here is that I'm going to lift this guy all the way up to right here. So the reason why I said let's assume Carlos, because I know that from here to here, I can actually measure that distance. So that distance here turns out to be, because I could measure it, shows that it's 0.65 meters. So that's, I have to go up and down. So now, let's start to look at this thing. So note, I could be in a state of positive work. What does positive work mean? It means that the way I lift this thing is that I think about it in this way. The weight of gravity is pulling it down. But what I do is that I push up. So this is going to be the force of me pushing up, and I'm going to call that force F. But now my displacement is then going to be in the positive direction here. So in other words, I imagine that I apply a force here and my displacement is going up. So positive work implies that one lifts the bar upwards, right? So it's going upwards. As a consequence, what does that mean here? Well, what that means here is that what is being done work on? Okay, so now we got to switch to the language of energy here. What is being worked on? What is being worked on? Is it the body? Or is it the bar? Well, you said that you wanted to go to the gym and work it off. So how do I think about this? So the question is it the body or the bar? In other words, the weights that work is being done on. The language gets really, really tricky. So now I imagine that I have a bench press. So here's my bench. And now here you are, or here's Carlos, right? I'm the skinny geek here. And what I'm doing with this skinny geek here is that I am going to lift this bar up. So I'm pushing up on this bar right here, and I'm moving it all the way up to right here. So what do I imagine here? I got to pick my system. So what's my system? I'm going to say that my system here is the bar. Right? Isn't that what we were talking about? We were talking about the force here. We are pushing up with the force to overcome gravity. We have to balance gravity up. So in this case, we see that the system here is the weight itself. So when I look at the weight itself, here's what I'm seeing here. There's two phases of the lift. Let me move this over here. So I could say that there's the lifting phase. In other words, you go up. So as you go up, we're seeing here is that there is work being done on the weight, which I'll probably just call the bar because you're in contact with the bar. So I'm going to say that this is the work on the bar. So what happens? You push. So if you're looking at the weight here, here's what I'm seeing here. You are lifting upwards. And if you lift upwards like this, I'm going to say that you apply force upwards, and therefore the displacement is in the same direction. So I can immediately come in here and say, okay, I did positive work. Why? Because I have a force and a displacement that are in the same direction. Therefore, this becomes positive work. Now, I have to bring down the weight. So if I bring down the weight, now I'm in the lowering phase. And in the lowering phase, I bring the weight down. So now let's look at the work done that you do on the bar. So in this situation, what do I find? My bar starts off here, and then I bring my bar down here. Now, how do I push on the bar? Do I push up or do I push down? Now, hopefully, you're not pushing down because then you're bringing this thing. And if you push it down hard enough, you might, I don't know, collapse your neck or something. You still want to apply a force upwards. But what you're doing with your arms here is you're bringing it down. So when you look at this thing, you can see here that the work that you do on that bar is negative. But you're still applying the same force and you're still moving it. So now there is negative work here. Negative work is done. So now, what's the net work done on the bar? Now we could say here is that the net work done on the bar is then going to be the work going up, right? I'm going to say I'm going to have positive work as I go up. And then when I come down, I have negative work going down. And if I apply the same force and I do the exact same thing, then this quantity is zero. Therefore, there is no change in energy on the bar. But we do not care about the bar, but the weightlifter. Because according to this picture, it's easy to say that there's no work done because the bar didn't change positions. It started and it ended at the exact same spot. But that's not true for the weightlifter. A human does work on the body. And how does a human do work here? So then we say here, when we talk about the work done by the body, by the way, this is what we typically call working out. What do we mean by working out? Your heart applies a force to your blood. And then what happens? Your blood now is displaced some distance. In other words, it has a displacement. So when you're looking at it, as you push the bar up, your body is doing work. And when you pull it down, your body is still doing work. So therefore, your body does work going up as well as going down. And because the force and the displacement are the same, they do the same work here. So now the work of the body will then be the work up, but that is still positive. But now the work coming down is positive because you are still applying the same force to your blood. So therefore, we then say that you are doing double the work when you go up and down. And so in this case, we could then calculate what this is. So now this will be the force that you apply times the distance that it moves. So in this case, if we now lift, let's say that you lift 160 pounds. 160 pounds is 710 newtons, which is roughly around 700 newtons. So for Carlos, the distance is 0.65 meters. That's just the value that I measured in lifting here. So if I put this all together, then the work of the body then is going to be 2 times 710 newtons times 0.65 meters. And the value that I get here is that I get a value of 920 joules. So this is the work of your body for a single lift. Now, let's put that all together. If we put this all together, here we go. Now what we want to do here is that we want to convert this single lift into calories. So how many calories did you burn on a single lift here? So then the work of a single lift is equal to 920 joules. But now if I convert that into food calories, we're going to say that 4,200 joules is equal to 1 food calorie, 1 big C. So check this out. This turns out to be 0.238 calories. So if you lift 160 pounds one time, right? This is telling me that if you lift 160 pounds once, you've burned off 0.238 calories. It's not even 1 calorie. It's in fact, it's like a fifth of a calorie. Now, here we go. How many reps? Are required to burn off the 1160 calorie milkshake? Well, here we go. So the number of reps has to be the number of calories of the shake divided by a single lift burning of calories here. And I get a number that's around 5,000 reps. Huh. So check this out. That's a lot of reps. You enjoyed that milkshake and then you felt guilty and you decide that you want to go in and work off all those calories. By the way, this is a little bit of a white lie. Your body, and I should really say your brain takes a shitload of the calories. Your brain takes about 25% of the calories to operate your body. So if you had about 5,000 reps and then you reduce by 25%, it turns out that this is going to be around 3,700 reps still. You still have a lot of reps to do. Is it worth counting calories? From this naive calculation? Absolutely. Do I think you should count calories? You know, some people can count calories and lose weight. There's other people that can't do it. I am no expert. I wouldn't doubt it if you're a much better expert than me. But either way, maybe counting calories might be the way. Maybe instead of a shake, you choose for water instead. Who knows? Anyway, I think that's a fun calculation.